Alright, we're now going to discuss force diagrams and a few problems that consistently keep coming up. Notice that I've drawn a few pictures here. It's a person standing, pushing up against a wall. We have a person in a boxing match with some type of bear panda thing. The bear panda thing obviously winning and crushing the person by sitting on them. We have a person on a rocket pack, and we also have a person running on a treadmill versus running outside. Okay, so we're going to look at first the person leaning up against the wall. Whenever doing a force diagram, make sure that you draw the forces on the object that you're talking about. So you have to be very careful and think about this carefully about what forces are actually pushing on this object. Now Newton's three laws are also going to come into play here, going to help us a little bit, but we will talk about that as they come up here. Alright, so first we have the person pushing up against the wall. Let's start off with the basics. Obviously this person is on Earth, so we're going to have force gravity. The person is obviously standing on a solid ground here, so that's going to go up. I'm going to draw these just about even because I know that this person is not accelerating up or down. Notice how I've looked at this in terms of up and down and not necessarily as in terms of a whole yet. Okay, because you can be accelerating to the left and right without accelerating up and down. Next, I of course have the wall pushing back on the person this way. And I'm going to call that force normal as well because that's a solid object pushing there. Now I tell you what, as I look at this picture right here, this tells me that this person is going to have to accelerate to the left because it's unbalanced. This is where Newton's first and second law come into play. So I know there's some force here, so I'm going to draw that there, and then I'm going to think carefully, what might it be in this situation that causes the person to lean forward like that? Well, if they're pushing up against the wall, that's going to be the force of probably their muscles on the person. That's what's actually pushing them this way. Now you might be confused. You might say, what about the force that the person's putting on the wall? Well, that does not belong on the person. Obviously, this is a second object here, and with its second object requires an entirely new force diagram. So if I wanted to write that, I could draw the force of the person on the wall. This, of course, being the third order pair of this one, because if I use the subscript for force normal here, that would be the force of the wall on the person. And all that really is the electrons in the hand and the electrons in the table pushing off of one another. Alright, let's continue. So now we have the person in a boxing match versus the panda in a boxing match, and as you can see real quick, they're not exactly making contact with one another yet, so it's just going to be very easy. The force of gravity pulls each of them down. Of course, I need to make sure that the panda, having more mass, has more gravity. Also, the Earth is going to push them up, force normal. And because the panda has more mass, pushes more against the Earth, and therefore the Earth pushes up harder on that particular panda. Now, let's say they were to hit each other. Okay, let's say the panda punches the guy in the face, or let's just make this easier on ourselves since we're drawing these forces from the middle. Let's say the person shoves the panda while the panda shoves the person. Now what that really is that's the force of the electrons in the hands pushing off of one another. And you'll get the force of the panda on, let's go with boxer here. Alright, and then I have to draw the exact same size over here because of Newton's third law. This is the force of the boxer on the panda. And these are your third order pair right here. I could see from this situation that this person is going to accelerate this way and that this panda is going to accelerate that way. Now, assuming that they both started with an initial velocity of 0, we know which way they're going to end up on the end. And you can be pretty darn sure that due to this right here, that the person is going to accelerate quite a bit more than the panda. And now I bring up this situation because we're having a lot of issues with the force compression. Now, when I do a force diagram here, I need to be very, very careful of which object that I'm talking about. Am I talking about the person being crushed, or am I talking about the panda? Both of whom are not moving, so I know they obey Newton's first law. Let me begin with the person. Okay, now you might say the person is getting compressed, and therefore they get force compression on them, and that's actually not accurate. If we look carefully here, we'll see that gravity still goes down, should be the same as before if I drew it correctly. Force normal, I'll save for a second. Is another force going down, or the force of the the force of the panda on the boxer again. And now I saved the force normal for just a second ago so that I could show through Newton's second law. If I've got these two down, then force normal should be bigger than just force gravity, because we'll also have the force of the bear on the boxer, or the panda on the boxer. So I should draw that. Let's see if I can draw it a little bit bigger here. Draw that twice. Well, it's about the size of those, and that would be force normal. All right, now let's come over here and look at this rocket. Okay, so we got a person strapped to a rocket backpack here, so let's do the force diagram on them. We should have the force of gravity down, naturally, since it's on Earth. Okay, they're not moving yet, so we're just looking right as they're taking off, so there's not friction yet. There will be a little bit of force normal, because it's still on the ground, just a little bit, just for a small amount of time until that rocket takes off. Okay, we're going to have, let's think, force tension, no ropes, force compression, no. The force now, this is the random force again of rocket on the person, and that's going to take them going up that way. So that'll be the force of rocket on the person. All right, last one to look at here is a person running on a treadmill versus a person running outside. You've noticed when you run on a treadmill, it's actually easier to run on a treadmill. So let's begin with the person outside here. We have force gravity, force normal, as we typically have. Okay? And now we look at it's moving, so there's definitely going to be primarily air friction that's pushing against. That's actually what mostly keeps us going. Now this person is going to travel at a constant speed. That means I need to balance out this other force with the force going forward. That should have been more to the right, but that's fine. I'll use a random force here, and let me think about what is it that actually pushes a person forward. Well, it's their muscles, so I'll put force of muscles on person there. Okay, now if we look at the person on a treadmill, the force of gravity is going to remain exactly the same. Force normal should remain exactly the same. What changes in this situation? Well, the person is running just as fast, but they're running relative to the ramp, and they're not running as much relative to the air around them, which actually means that this force friction, which usually pushes quite a bit more, is going to be less. And since it's less, the amount of force necessary to put forward, I did the same thing again, of muscles on person, well, it's still going to be there, but it's going to be a lot smaller. And that's why it's easier to run on a treadmill versus running outside.